Hey everybody, welcome to another webinar in our 2021 Smart Building series. Hope everyone is doing well out there. And today we are talking about tagging with AI to enable data-driven applications at scale. So really interesting talk today. I know I'm going to learn a lot because I'm joined by Jason Coe from Mapped. Welcome, Jason. Hope you're doing well.
Hi, James. Thanks for having me. I'm really excited to talk about this.
Yeah, and I'm excited to hear it, and I hope everyone out there is too. I just wanted to start by saying a couple of things. First of all, we want to make this an interactive session. So if anyone does have any questions, we'd be happy to take them. But first, we're going to go through a presentation. It should take about 25 minutes. If you want to put your questions in the Q&A, if you look on your screen, you'll see that at the bottom. And then after the presentation's finished, we'll be able to field those questions. Beyond that as well, we are recording this session, so I'll make sure that that is available, and we'll be posting that on our website and on YouTube probably later today or tomorrow. And then that will be emailed to everybody who's attended. So yeah, I think that's pretty much it. So let's get started. For those of you who don't know, we actually produced a report earlier this year about AI and machine learning for smart buildings. It's something that, of course, as an analyst company, like we've been really interested in for the last couple of years, and we felt it was sort of time to try and look at the landscape of what is happening, which companies are really engaged with artificial intelligence software, and importantly, ask a couple of questions really. Right, one, not just how AI is being applied to buildings, commercial buildings, but also, what is AI and what isn't, right? That was something that we've seen, and from feedback that we'd had from people, in the market, that, often it's sort of used as a buzzword, a marketing term, rather than, actually really having a deep understanding of what it is and how it can be used and how it can be applied, which of course is why I wanted to talk to Matt today, because I think they have a really interesting solution which uses AI in a very neat way to provide value, and Jason's gonna talk about that in a minute. So anyway, this was the landscape diagram from the report, where we've categorized some of the companies that are providing software, AI software and machine learning for the built environment. And then if we go on to the next slide, you'll see we made an assessment of what we think is currently the global market for this type of software in smart commercial buildings. So last year, we estimated that was going to be about 1.1 billion. And I don't think it's a surprise to anyone that this market really is growing. We're seeing a lot of applications for this type of software to optimize commercial buildings. So it really is an exciting time, I think, to be in this area. So I think with that little intro, I'll hand over to Jason. Yeah, Jason, please go ahead. Maybe give us an introduction to yourself and the company Mapped. That would be great.
Of course. Yep. Thanks for setting up the stage, James. I am Jason Coe. I'm Chief Data Scientist at Mapped, and Mapped is building a data infrastructure for commercial and industrial IoT. We focus on data discovery, extraction, and normalization for all the data available in those IoT systems for applications. And today, I'm going to talk more about how we use AI to automate the process of handling those data and normalizing them into a single model. So let's dive into the talk. So the audience probably joined this talk because you recognize the potential of the building data there are many, just so many applications that the people want to deploy over their buildings and their systems, but they need a lot of different data sources. Like if you want to estimate the air quality, you want to understand the current status of the HVAC systems, you want to get the occupancy from the security systems, you want to check whether people have used the elevators or not. And different applications need access to the different subsystems, and it is just complicated as it looks like this. And Mapped instead provides a single gateway for all the data in buildings as a single API, and we do all the dirty jobs of taking data and normalizing the data and so on. And you can imagine the current situation is more complicated than accessing those subsystems, because every building is different. They have different conventions, configurations from different vendors for different purposes. The list goes on. So this is how it looks like when you look into the building management systems or tap into the BACnet to get all the entities from those systems. From those three buildings, you can see different conventions, and one building is a CAV-based building, and another one is VAV-based building, and the other one is quite unknown based on the conventions. This is even worse, even because even in a single building, there can be no conventions, and there can be a customized device installed after 10 years of the building deployment. So we really need a single view other than those heterogeneous metadata to represent the context of the individual systems. So Mapped proposes an ontology that is extending Brick for representing everything in buildings. And in Brick schema, we have top three classes of equipment, point, and location. And those top classes are extended to actual concepts that application need to understand, like the air handling unit, VAVs, or floor, room, space, restroom. And for points, there can be zone air temperature sensor, supply and flow sensor. The list goes on here again. And on top of those type hierarchy, Brick can represent actual relationships across those entities that applications want to contextualize. So we identify those from actual applications, and those are canonical and useful across all the systems and applications. Brick Schema is a community-driven open source. You can get an access to it when you visit the website. There are a lot of documentation if you want to educate yourself with it, or I can answer any questions at the end of the call as well. And the schema itself has been rigorously validated through a formal process, which means that there's no friction across different concepts and more stable to use. It is extensible to new concepts, and it is expressive because we represent everything in the graph. And applications can rely on it for getting their data. And what Map does on top of Brick is to introduce a few new concepts like people. People has been recognized as very important for certain applications, and which I'm going to exemplify in the next slide. And there are more classes we want to represent, like secure systems, conference devices, and so on. And we're communicating with the Brick community to augment the schema on the line. And we also have the concepts of identities management. We are integrating different subsystems for all the buildings, meaning that there can be duplicated things across different systems while we want to relate them with each other across the systems. So here's an example graph that you can get from a normal building. You can see air handling unit, VAVs, zone, rooms, and certain sensors like zone air temperature sensor, supply airflow sensor, and so on. And this is HVAC and the relationships between HVAC systems and structural data. And with Brick, we can identify types of those entities, like VAV101 is a VAV, AHU1 is an air handling unit, zone is an HVAC zone, and so on. This is typically known as a tagging problem because you want to define the attribute of those entities. There are different ways to define the attributes for those, but in Brick, we define types for those entities, like the object-oriented programming concepts, like you're instantiating those classes. But more importantly, not over those tags, relationships are really important for contextualizing those concepts. Like air handling, this air AH1 is feeding air into the VAV, and this VAV 102 feeds air into the zone, which is composed of those two rooms. And if you want to get any information about the VAV, you want to get you want to access the related point. So understanding relationships is the key in this mapping, and it is more important when you introduce other subsystems or other sets of the data with HVAC systems. Like if you there's a person, Jane Doe, who owns a corp batch, which has been observed by access history status, which is a point of access card reader, which has location of the room 102. In this way, you can track this person has been located in this room, and we can provide more context over the entire building across different subsystems. So to provide this single view over all the different data sources, MAP has a single automated data pipeline. The first stage is to discover and extract all the things in the systems. We have our own universal gateway that can talk to different building protocols such as BACnet, Modbus, KNX, and so on. And that is, it is extracting discover and extract all the entities and convert them into an intermediate data representation and publish it to our cloud service and do all the smart things out there. Note that our device is not limited to the physical device, but the exact software piece can be running inside the Docker container, as these days many building management companies or building owners have their own Docker containerized environment. Or we can also deploy it in the host deploy it in the cloud and connect it to the customer buildings using a site-to-site VPN securely. With those ways, we can ship the intermediate raw data into the cloud and do all the AI stuff inside our cloud service. It is interacting with the data and domain experts to perfectly and quickly normalize all the data into this ontology as I presented in the earlier slides. Once everything is normalized, the users can visualize the data, how the data is flowing from actual data sources into subsystems and applications. And in that way, the data owners can have a holistic view of how the applications are using which data easily in a single view. This is enabled by our fine-grained access control over those data. The data owners can control how the location and the types of the systems that they want to share with individual applications, whether it is third party or third party. So once everything is set up, individual applications can access any data through a single GraphQL API. GraphQL has been, for those of you who are not familiar with GraphQL, was developed by Facebook initially, and it is widely used by modern web technologies because it is very flexible but useful for applications, because the applications can any web applications or backend applications, that they can define what kind of data they want from the data source and define the shapes of the data and define the relationships. So it is very flexible and powerful. So as I mentioned in the earlier at the beginning of the talk, we are going to focus on how the mapping is automated by AI at Mapped. And I have been talking about the machine learning metadata normalization with machine learning in the past, I don't know, 5 or 6 years. And I actually had a presentation in this memory webinar a couple of years back, but I'm still talking about it, and that is because it is not an easy problem. People want to really solve the problem, and I want to explain how Mapped is advancing the technologies for achieving that at scale. So let's define what the problem is. So the metadata mapping problem is like this in an example. Let's say there are 3 object names or entities you got from the BACnet or any other BMS systems or protocols. The first thing you want to know is the types of those things. You want to say the top one is the zone air temperature sensor, and the other one is occupancy command, and AHU1 is, of course, an air handling unit. But you can see that there's much more information other than just those types. You can see that RM101 is a type of HVAC zone, and VMA101 is a VAB controller. So you want to get as many entities as possible. And as I addressed earlier, more importantly, understanding the relationships is the key. We want to also say that this zone air temperature sensor is a point of the VAB, and that VAB is feeding air into the room. And these relationships exist in a single entity name, a single point name, but the relationships across those objects are interesting as well. Like this occupancy command is sharing the same VAB, so those two are co-located and used for controlling the VAB. And this air handling unit is feeding air into the VAB. So how do we know those types and complicated relationships with machine learning? So this is the problem that has been tackled by many different researchers throughout the last 5 or 6 years. Various AI methods has been proposed, like point name analysis and time series clustering for understanding the types or data type or units, and causality and correlation learning for understanding the relationships across different entities. But those have not been enough, because those algorithms and AI models are not scalable enough for helping to normalize all the buildings out there. So why is it very difficult, and why people are still studying how to mitigate the problem? So the first challenge is the lack of label data. Once you tap into the building, you have no idea what the individual keywords mean and what are the relationships across entities are. And if even if you want to label them and construct a graph, having a domain expert understanding the system and the ontology and all the IT technologies is very expensive in terms of the hourly rates or and time that it consumes to convert those into a normalized format. And all the buildings are different, and this is related to the lack of the previous problem of lack of label data, because once you label, even though you can label one building very completely and comprehensively, you cannot reuse the E4 across different buildings because they have different conventions or different systems, or have just different sensors within the single system. So any machine learning models really do not scale well. And the relationships that we need to know from different entities are really complex. And not a single, we have noticed that not a single algorithm can do everything for all the complex relationships. Like sometimes we're interested in causality or compositional relationships, or just the types. To mitigate those problems, I'm gonna give you some high-level overview of active learning for reducing the problem of the lack of label data, and transfer learning to explain how to utilize different buildings data, and ensemble learning for utilizing various machine learning models all together. So this is mapped approach, and this is a workflow end-to-end. From a new building, we want to train a machine learning model, multiple machine learning models in a directed acyclic graph by exploiting other known buildings as well. And in that process, we are interacting with domain experts to fill out the gap in the existing data set. And final outcome of the models can be output as a mapped graph, which is accessible from a single GraphQL API. So what is active learning? The question that active learning is trying to answer is, what is the most efficient way of acquiring labels, given that domain experts are so expensive to just label the data sitting on the desk and looking at the monitor and mark individual keywords. So here's a general process for active learning. First, train the machine learning model, give any given label data. If it doesn't matter if it is just have 5 or 6 sensors labeled, you can train that and infer the rest of the data and pass it to the domain experts. And domain experts can pick the pick the examples with less confident results and put labels and give them back to the machine learning model, and then repeat the process. Here, the goal is to not label redundant examples, which is a waste of their time. Given a medium-sized building, it typically contains 5,000 to 20 data points, and many of them are probably just a zone air temperature sensor. So labeling 100 zone air temperature sensors does not improve the inference mapping accuracy for supply of flow sensor or CO2 sensors and so on. So we want to pick the exact points that are not not have been labeled in the past. For better active learning at MAP, we have various statistical metrics from these different machine learning models, like tagging utilization or confidence score from individual machine learning algorithms. So we combine all the heuristical and statistical metrics for picking up the non-redundant examples every time. We also have a highly optimized labeling tool for reducing the time for domain experts to provide a label. It does suggestion based on the rules and try to infer based on current understanding. And domain experts can just type a few keywords for the suggested items. And it is estimated to take 30 seconds to label just a single object, other than 3 to 5 minutes as reported in other places. So now we know how to reduce the effort for acquiring labels, but how do we exploit other buildings' data for a new customer building? So this is also typically known as a difficult problem, because different buildings have different patterns in both point namings or time series pattern, because there can be different occupancy schedules or usage patterns. So even though you know what's happening to the existing buildings, you cannot directly apply that knowledge to the new building. In the machine learning research area, there are several known ways to resolve the problem, like shifting data distribution from known buildings to the new building, so that they look more similar, and machine learning model can train from the known buildings can work better for the new building. Or you can pick only the common features from the known buildings, so that unknown features do not damage the performance for the new building. And of course, if there have been any uncommon patterns observed from known buildings in the new building, we should ask the domain experts as well, because if CO2 sensor, for example, has not been observed in the past buildings, we should be able to identify that and ask the domain experts for the new building. At MAP, we employ domain adaptation models that can suppress the uncommon features that is damaging the performance of the model for a new building. And with that common features, we can also identify the new features for the new building. And we also do similarity analysis across different buildings, so that we don't have to train hundreds of thousands of buildings for the new building, but only the useful buildings for mapping the new one. And last but not least, how do we ensemble various machine learning models? One machine learning model has a view infer this is a zone temperature sensor, but another one infers something as a supply flow sensor. And if that is happening when we have multiple machine learning models, and there are several frameworks for integrating those different machine learning models. And the common frameworks for this is voting selection, or decision tree, boosting algorithms, and so on. Or more generically, directed acyclic graphs can define the dependencies across different machine learning models in an order. So at MAP, we have flexible DAGs based on customer requirements, even though we can configure different set of machine learning models per customers. We often use the most comprehensive ones for individual customers because that is often the superset of everything. But still, this is possible because we learned all the priorities over different machine learning models. So one machine learning model's results can be used for another machine learning models, or overriding other machine learning models results. For example, like if you want to understand the relationships between VEVs and AHUs, you first need to understand what are the airflow sensors or discharge air temperature sensor to understand the relationships. So those type identification should come before actually learning the relationships across different entities. So coming back to the high-level view, I have explained we are employing active learning and transfer learning and ensemble learning for generalizing all the different machine learning models for different buildings. To summarize what we do at Mapped end-to-end, we believe applications need a single API with a common view of the entire world of our different subsystems, and we are utilizing Brick to represent everything within an ontology. And those data are discovered, mapped, normalized, and being served in the same pipeline through our gateways, machine learning, and control planners, and then GraphQL API. And the complicated machine learning problem, we are trying to solve the problem by employing active learning, transfer learning, and ensemble learning of individual machine learning models. So thanks for attending the talk today. I'd be happy to answer any questions, metadata normalizations or Brick schema, or any other AI technologies in smart buildings. Thank you very much.
Thanks, Jason. That was really, I thought that was, like a really insightful presentation, because I mean, what we're talking about here is, a very complicated problem, right? Which I think you did a good job of framing. And then, and again, like this, the techniques you're using, again, this is a complicated topic. So thank you for trying to kind of put that in a short presentation, because I know it can't be easy to explain some of these concepts. And again, as Jason said, like anyone out there, feel free to ask questions. I guess, whilst we have like this expert online, if you want some sort of more technical questions about these approaches, can ask those kind of questions, or indeed anything more high level, I guess, like about as Jason said, and about Brick, or how they're using Brick, or indeed, more about sort of how AI can be applied to buildings in general, commercial buildings. So yeah, maybe, I mean, I know we had one question come in, and I can just go through that in a minute, but so from my side, there's a couple of things I was really interested in. Certainly some of those methods that you mentioned, I think I wrote them down: point name analysis, time series clustering, correlation learning, again, as ways of trying to solve this problem that we all know about, right, with having all of this data in the building, which hasn't previously been normalized, right? And obviously that's what you guys are trying to do here: normalize that data so it can be used effectively. What is now changed, do you think, Jason? Like, with this new development of these different
Sure.
algorithms, like, yeah, how has sort of the software gone on to help you guys solve these problems?
Sure. individual algorithms are doing very good job at handling data for individual buildings. I'm not proposing we need to discard those algorithms and develop new ones. But when you develop and improve and actually deploy those models, you need to consider the scalability problem, because those models usually do not generalize well, meaning that you need a tweak of those models. Like for at Math, for example, I talked about domain adaptation, and I presented a point name analysis algorithm several years back, and we updated with by introducing a common feature layer that is that is penalizing different patterns across different buildings, and only cherry picking the common features. So the individual algorithm can remain the same, but it is utilizing a better feature, the useful features from other buildings for the new building. So here, what I was trying to address was when your focus should be on the scalability, even though you want to still use the best performative algorithms out there.
Mm-hmm. Yeah, no, that's a great point. And again, it's sort of like, whilst I think that a lot of these buildings generate a lot of data, which is great. And again, I think you're solving that big issue of being able to normalize all that data. Again, like AI, it requires all of this data, right, to be able to train good models.
Yeah. I mean, if there is a big data like what Google does for image classification for building normalization data, there's no problem with scalability issues and so on, because all the data are represented enough for any buildings out there, which is not the reality for now.
Yeah, exactly. Yeah. Okay, we've got sort of like 4 questions or so come in, so I think it's best that we take those now, and then maybe at the end we can wrap up with some sort of more high-level advice that you could give to people out there. So I'll just take them in the order that they came in. Actually, I think Sean has sort of already answered this, but I think it's an interesting question, so it's probably worth sharing with the whole audience. You talk about extending the brick model to other systems. With this extension, will this extension be shared back to the brick project?
Yes, of course.
Yeah.
Oh, yeah. Is the end of the question? Sorry.
Yeah, no, just to say that, like, that's basically what Sean said, that all mapped extensions are shared, but there may be some lag in that time between your customers getting it and the brick consortium, because it needs to be, I guess, voted on, right, by the brick consortium.
That's correct. So we don't want the friction between the standard out there and our development of the ontology. So we want to provide our thoughts of the model as soon as possible back to the community. But we need to validate it is really working for our customers before making a concrete proposal to the brick community. So there is an inherent lagging between our development process and the contributing back to the brick community, but we want to eventually synchronize them as soon as possible.
Yeah, no, and just sort of extending on that question, I think was really interesting that you about this extending it to identity, but and you use that access control example. Yeah, I think that's just a great idea, right? It really adds extra usefulness to that data, right? If we know where people are, not so much that it matters who the person is, perhaps, but more about what occupancy is and how the building is being used. So, no, I think that's a great development. I guess my question on that, though, is it's sort of access control is something we know relatively well, right? We've tracked that business, and quite a few of the suppliers there sort of aren't, let's say, that quick at adopting open standards. I mean, do you think that could be an issue, getting data out of access control systems?
That's a good question. First, usually not all the access control systems, but modern access control systems come up with the structured data in a way, even though they are not aligned to a specific ontology, but some way that the vendor provides. Even if that's structured in that way, we can easily translate those into a target ontology like brick, because if it is structured, it is just field-to-field mapping or relationship mapping.
Right.
And in that case, the data analytics applications can easily run on top of some common data infrastructure like map, because it is one-time effort for mapping.
Mm-hmm.
And if it is traditional systems like inside BACnet or some closed network with a proprietary protocol that needs, again, the metadata mapping process like this, which is a little bit more difficult than just field mapping, but it is doable.
Yeah, no, good point. So next question is, I'm seeing DAG for the first time. Could you please explain why you're using it in this case?
Sure. DAG means that so let me, can you see my mouse cursor here?
Yes, I can.
Okay, so this is an example DAG, this directed acyclic graphs, and individual node is a machine learning model and has a dependency in this way. So this is directed in this way, but this is acyclic. There's no cycle in the graph. This is useful when we need a workflow across different nodes here in the machine learning models. So this machine learning model may infer the types of those entities, like this is a zone temperature sensor, this is a CO2 sensor, and then this machine learning algorithm that is trying to learn the relationships between air handling units and VAVs can utilize that information that was not available without this machine learning model for finding the correlations between the airflow rates and air temperature changes for understanding the relationships. And it can be complex as much as possible given a cyclic graph, and this is intended to be a simplified mathematical problem of dependency resolve and so on. Mm-hmm. I hope that answers, but please follow up if you have any questions further.
Sure, I'm sure they will if they want. Next question here is also an interesting one. Any improved hardware capabilities that can complement metadata labeling?
I'm thinking. That's a good question, and it depends on the customer use cases, I think. Mm-hmm. So in our case, we have had no problem of pushing many of the data in our secure place in the cloud. But if the customer wants the on-prem based deployment scenario, we can make a bigger hardware and with a better computing power, shipping with the machine learning models and data to better perform without accessing to the cloud. Mm-hmm. So it really depends on the customer use cases, but we believe that smaller device is better for a wider deployment.
Yeah. Okay, next one here. Could you give a quick overview of how you take a point from a previously unknown system, let's say a real-time location position, and make it configure to the mapped brick schema regime?
Sure. So that is we have several ways to ingest all the data sources out there into our pipeline, and one of the ways that this universal gateway that I presented earlier, which has a pre-encoded mapping from all the protocols into an immediate intermediate format. So if it is if you tap into the backnet, you can check the backnet unit, backnet object property, object types, object names, or vendor names, and those are normalized into our intermediate data structure. And same for Modbus and KNX and so on. But of course, those protocols do not represent everything in the world. So we have a separate workflow for developing the connectors for individual data sources, which has a template and which can be reused across the instances of those connectors. So if there's a weather station with a single endpoint, we quickly develop the connector that is mapping the raw data into our immediate data structure. And then once it is developed, you can deploy it to any instances using that system. So we are using templates and protocol mapping for the initial discovery.
Mm-hmm. Yeah, no, nice overview, thanks. And then there was a follow-up question about that. Well, it's sort of slightly different, but does MAP manage APIs, maximum number of calls, etc., which user can access which system? So I guess, like, you know, how, if let's say sort of I think you talked about, you showed a slide, right, with the whole offering, but at the end, the data visualization, is there a way of getting that data out of your system via an API?
So if I understood the question correctly, is there a limit on the usage of the API, or
no,
can you clarify that?
How you manage APIs.
Jason, I can take that question if you want.
Oh yeah, that'd be nice. Thank you.
Yeah. So from an data consumption standpoint, the API that we offer through our cloud is the same as any other API. So it is a metered API, meaning that you're paying on a per API call. We do some things around how much data is getting returned if you're querying the value of for example, a single thermostat, versus if you're trying to, get the hour by hour average across all the thermostats in your portfolio of 1,000 buildings. Those queries have different cost models, but we try to keep the cost as low as possible on the APIs. As far as what you can take out of the platform, we support both a query-based model, so you can reach in with a query like Jason's showing on the right-hand side here.
Yeah, that unified
and
access.
make a single query and get data out. But you can also do what we call live queries, which are queries that you sort of push into our system, and anytime data matches it, you get sort of a webhook type callback for data that matched that. So you can basically subscribe to certain queries and get notified when those happen.
Nice, thanks, Sean. Next question here. This is very interesting. For a typical, let's say, 5,000 point building where there is good access to the BMS, how long does the mapping process take? And what levels of accuracy or completeness are you obtaining in building the graph or relationships? Yeah,
I'd be happy to answer that question. Typical building, if you do not have any pre-labeled data from other buildings, it typically takes 1 to 2% of the data to be labeled in our past experience. It is converted into the manual effort of several hours, and it is optimized through the machine learning interaction, as I explained in the active learning framework, like this. It is an interaction with the machine learning model, ending up in several hours for converting those. And by labeling those 1 to 2%, you can achieve 96 to 98% accuracy. And if you employ other buildings' data with common patterns, we see a 20% bump or 20% to 50% bump based on the similarity of the buildings which is taking D for the half or less.
Mm-hmm. Okay. Another question here. Can you please talk a little bit about your business model? Is it a SaaS or platform as a service? And how do you deal with the building configuration changing and updating?
I can answer the question, but we have Sean Cooley, our CEO, in the call, so I will let him to answer that better.
Sure. Yeah. So we are a software as a service. There's, as Jason said, a hardware component that can be deployed on-prem if necessary. What we find is that for most IP converged systems, the hardware component's unnecessary. But if you have older RS-485 or RS-422 bus type systems, then the hardware component becomes valuable. The software that's running in the cloud, the sort of it kind of walks a fine line between platform as a service and software as a service. The as a service piece that is in the cloud is what does all of the normalization, data retention, and APIs for querying, as well as access controls around data, so that you can grant access to vendors or to tenants inside of your building or what have you. From a cost standpoint, we don't publicly share cost right now, but I can say it's sort of an all-you-can-eat type model on the data that you bring in. So we don't charge by the point or by the square foot or anything along those lines. We simply charge a flat fee per building on the data production side. And then I talked earlier about the data consumption side being on a metered basis. And then as far as how do we deal with building configuration changing, so we refer to this as the day 2 problem. It is a big point of focus for Mappd. What we have up in the cloud, we refer to as a living graph. So it is a near real-time representation of everything we are observing out on the edge, out in the buildings. And that means that as devices change IP addresses or change BACnet IDs or serial bus IDs, as firmware is upgraded, as equipment is removed and new equipment's installed, whether it's a direct replacement or sort of a sort of similar type of equipment replacement, we try to reflect that very close to real time. Maybe a couple of hours, but try to reflect that in the graph at all times. And so, this produces a lot of other interesting issues, about us keeping stable IDs in the graph. You want to make sure that if a device changes IP addresses or BACnet IDs, but it's still the same device, that any software that was built on top of that graph continues to recognize the device as the same, actual device and doesn't just get, random new IDs generated and stuffed into the graph. And so lots of good fun around keeping the graph up to date with what's in the real world, but absolutely not just a snapshot in time for what we produce.
Great, that's a great answer, thanks. Time for, I think, for a couple more questions. Thought this was an interesting one. How does Mappd service compare to a traditional MSI master systems integrator scope of work? Yeah, I mean, I guess, are you automating some of that process?
Yeah, I can take that one as well. It is, from a typical MSI standpoint, there's usually a target in mind, right? I have this particular application or this particular function that I'm looking to produce, or looking to feed data into, and the MSI will do the heavy lifting of going in and discovering what's currently there, and sort of mapping that into that end state. Our end state is brick, as Jason described, and so we are heavily focused on automation and machine learning around taking sort of the chaos of the real world and mapping it into that brick end state. And so, because we are entirely focused on machine learning and automation, I would say that in general, we should be significantly less expensive than an MSI. But I want to be clear that we do not replace sort of the initial commissioning of systems that has to happen still through MSIs, right? Somebody still has to go in and put all the components in there, connect them up, do the programming in whatever control systems are in place. But we then take that state and turn it into Brick to allow you to then generically build applications and dashboards and FDD and other functionality on top of that Brick normalized standard.
Yeah, no, that's a good point. And there's kind of like a follow-on, so we sort of take this as our last question. And actually, I think an important one. Is there any way to detect tampered edge nodes? Someone changed the device? I know there's obviously, it's a very topical issue with some of the cybersecurity breaches we see.
Yeah, I'll assume that they're referring to our edge gateway. I
don't think so, actually. No, just sort of things in general, but yeah.
Yeah. So it's I would say that Map's focus is not on that sort of like I would bucket detecting edge device or sort of field device tampering into an FDD type model, right? That's the same type of you're looking for anomalies, you're looking for change in behavior of a particular device, and you can absolutely build something like that on top of our platform. From our platform's perspective, we obviously do quite a bit to secure our edge gateway to make sure that it's not tampered with. And so, the edge gateway is as locked down as can possibly be. It has signed firmware images and secure boot and a hardware enclave that we store certificates in, and lots of things to prevent sort of tampering of our edge gateway. But as far as other devices, it really becomes an anomaly detection model that needs to be created, and it's not something that we do, but you can absolutely build that on top of the data that's coming out of the Mapped platform.
Yeah, no, it's a very good point. Yeah, I mean, anything else that you guys want to finish with? You think that we haven't covered, or something that has popped into your head?
Jason,
no?
Anything on your side?
I'm good. Yeah.
No, okay. I mean, again, thanks everyone for the questions there. If we didn't get to your specific question, or indeed if you got any questions for Sean or Jason about their business, or wanting to get involved with that, or Brick. I know obviously, Jason, you're heavily involved in Brick as well. So there on the screens, Jason's email address. Yeah, and I just obviously to both you, Sean and Jason, I really appreciate you taking the time to go through this today. I think it's super interesting what you're doing, and as I said, I think at the start, as an example of someone using AI, it's to improve what we're doing with commercial buildings. I think it's just it's a great example. So really happy to host you today.
Thank you for having me, and Sean, James, and I'd be happy to take any questions offline as well. So, and thanks for attending this talk, everyone.
Great, and just a final word from me. If you are interested in the recording, that will be up on our website probably tomorrow, and you should be getting an email with a link to that sometime tomorrow as well. Yeah, and it'll be on YouTube. So feel free to share that with your colleagues, and if you found it interesting, you think they will. And just beyond that, please subscribe to our newsletter or our YouTube channel, and you'll get more information on what we're doing, videos we're posting on issues relating to commercial real estate. So again, thanks for listening. Thanks, Jason, Sean, and wish everyone a good day. Thanks a lot.
Thanks, James.
Thank you.